of the UPS. Let us collect the tools and equipment required to do this practical. Trainees Toolkit 1 set. Digital multimeter with probes 1 number. Safety gloves 1 set. UPS with battery and instruction manual 1 set. Procedure. Task 1. Measurement of the voltages at main input supply. Note: remove the power cord from the AC main supply before starting this task. Step 1. Turn on the multimeter and set it to measure AC voltage. Identify the 3-pin AC outlet socket that has to be connected as input to the UPS. Step 2. Insert the probes into the socket's opening. The black probe should touch the neutral, while the red probe should touch the live, hot terminal. Step 3. Ensure that the probes make good contact with the metal inside the socket without touching each other. Step 4. Read the voltage displayed on the multimeter screen and note it down in the tabulation. A standard household outlet typically provides around 240 volts of AC. Step 5. Measure the voltage between phase and neutral using a multimeter and ensure the multimeter reads 220 volts. Similarly, measure the voltage between neutral and earth using a multimeter and ensure the multimeter reads not exceeding 5 volts. Serial number 1. Name of the test point. AC input supply. Voltage. Remarks. Number 2. Transformer secondary. Number 3. Rectifier output. Number 4. Battery voltage. Number 5. UPS output. Task 2. Measurement of the voltages at transformer terminals. Step 1. Remove the cover of the UPS by unscrewing it using appropriate screwdrivers. Step 2. Plug the power cord of the UPS into the mains AC input supply. Step 3. Switch on the power supply. Step 4. Measure the input AC input supply between the phase and neutral. The terminal to which the power cord is connected in the UPS. Ensure that the same input AC voltage is displayed on the multimeter. Step 5. Identify the transformer with the UPS. Turn on the multimeter and set it to measure the AC voltage. Step 6. Identify the input and output terminals of the transformer. Step 7. Connect the multimeter leads to the input and output terminals of the transformer. Mostly, the transformer is step down. Ensure the transformer type by comparing input and output voltages measured by the multimeter. Task 3. Measurement of the voltages at battery and rectifier circuits. Step 1. Identify the battery terminals on the UPS where the battery is connected. These terminals are typically located within the UPS housing and may be labeled as positive or negative. Step 2. Turn on the multimeter and set it to measure DC voltage. Step 3. Connect the multimeter probes to the battery terminals, ensuring that the positive probe is connected to the positive terminal and the negative probe to the negative terminal. Step 4. The rectifier in a UPS converts AC power from the utility into DC power to charge the batteries and power the inverter. Step 5. Identify the output terminals of the rectifier. Usually, in a UPS rectifier circuit, you'll often find diodes or bridge rectifiers responsible for converting AC to DC. Step 6. Set your multimeter to measure DC voltage. Connect the multimeter probes to the output terminals of the rectifier. Ensure that the positive probe is connected to the positive terminal and the negative probe to the negative terminal of the output. Step 7. Note down the readings in the tabulation. Serial number 1. Name of the test: AC input supply. Voltage. Remarks. Number 2. Transformer secondary. Number 3. Rectifier output. Number 4. Battery voltage. Number 5. UPS output. Task 4. Measurement of the voltages at UPS output. Step 1. Identify the output terminals of the UPS where the power is supplied to your computer or other connected devices. They are typically located on the rear panel of the UPS with 3-pin sockets. Step 2. Set your multimeter to measure AC voltage. Step 3. Insert the probes into the socket's openings. The black probe should touch the neutral, usually the wider slot or ground, while the red probe should touch the live, hot terminal. Step 4. Read and note the voltage in the tabulation displayed on the multimeter screen. This reading represents the output voltage of the UPS. Step 5. Similarly, measure the voltage between phase and neutral, earth and neutral using a multimeter. Measure the voltage values in the other output sockets. Recap. In this video, we have discussed how to measure the voltage at various test points of the UPS. Hi everyone. In today's video, let us learn how to identify various circuit boards in UPS and monitor voltages at various test points. Objectives. At the end of this video, you will be able to: Number 1. Identify various sections of UPS and locate test points on the circuit boards. Number 2. Measure the voltage or waveform at various circuit boards in UPS. Let us collect the tools and equipment required to do this practical. Trainees Toolkit. 1 set. Digital multimeter with probes. 1 number. CRO 0 to 20 MHz. Dual channel. 1 number. UPS with battery. 1 set. Safety gloves. 1 set. Procedure. Step 1. Keep the power cord disconnected from main supply and open the UPS unit. Step 2. Identify the major sections on the circuit boards of UPS referring unit. Step 3. Trace the circuit and identify or locate the test points on the UPS by referring to the circuit diagram. Types of UPS. Online UPS. Serial number 1. Name of the section. Rectifier section. Purpose. The rectifier unit in a computer's UPS is responsible for converting alternating current AC electricity from the main power supply into direct current DC electricity. Once converted, this DC power is used to charge the batteries within the UPS and also directly power the connected devices such as computers and servers. Number 2. Step-down chopper. An uncontrolled rectifier converts AC voltages into DC voltages. The fixed DC is fed to the step-down chopper. The PWM control technique keeps switching frequency constant and also regulates duty cycle to ensure the MOSFET to turn on. In constant current charging method, current is set at a fixed rate. Constant current is achieved by switching off the chopper. The step-down chopper produces a lower average output voltage than the input voltage. Number 3. Relay unit. The battery is connected to the variable DC through the relay. Relay gives the trip on the conditions of overcharging and under-discharging. The relays will work as static switches. The switching of inverter is controlled through PIC microcontroller. Number 4. Inverter unit. The inverter unit in a UPS is responsible for converting direct current DC electricity from the batteries into alternating current AC electricity. The inverter unit typically consists of power transistors, MOSFETs, metal oxide semiconductor field effect transistors or IGBTs, insulated gate bipolar transistors, and changes the on or off intervals to create pulse waves with different widths. It then combines them into a sine wave. Number 5. Microcontroller. The microcontroller manages the UPS system by controlling various components such as battery charging and discharging, inverter operation, and power output regulation. It continuously monitors input power, battery status, output load, and other parameters to ensure seamless power delivery to the connected devices. Step 1. Connect AC main supply to UPS and measure test points voltages of each section and record in tabulation. Step 2. Prepare the CRO for measurements and check the output waveform at the oscillator section. Name of the section: mains to inverter change over section, battery status, indicator section. Test point: test point 1. Description or function of the section: AC mains input. Set the multimeter to AC voltage with an appropriate range and measure the voltage in the mains input voltage in 3-pin sockets. Voltage or waveform. Test point 2. Rectifier DC output. Set the multimeter to DC voltage with an appropriate range and measure the voltage across the output of the bridge rectifier with correct polarity. Test point 3. Battery voltage. Set the multimeter to DC voltage with an appropriate range and measure the voltage across the battery terminals with correct polarity. Test point 4. Battery status indicator section. Look for LED indicators on the front panel of the UPS unit. Typically, a green LED indicates that the battery is fully charged and in good condition. A yellow or amber LED might indicate a partially charged battery or a warning state, suggesting that the battery might need attention. A red LED usually indicates a low battery condition or a fault that requires immediate attention. Oscillator and driver section. Test point 5. Input to regulator IC. Set your multimeter to the DC voltage measurement. Identify the input terminals of the IC regulator on the UPS circuit board. Connect the leads of the multimeter to the IC leads with the correct polarity and measure the voltage. Test point 6. Regulator IC output. Set your multimeter to the DC voltage measurement. Identify the output terminals of the IC regulator on the UPS circuit board. Connect the leads of the multimeter to the IC leads with the correct polarity and measure the voltage. Ensure the voltage in the multimeter is the desired output with a constant. Test point 7. Oscillator output voltage AC. Observe waveform using CRO. Identify the oscillator circuitry within the UPS. Connect the oscillator probes across the output of the oscillator circuit. Adjust the settings on the CRO to properly display the AC waveform. Test point 8. Triggering pulse input to upper bank driver AC. Identify the triggering circuit within the UPS. Connect the oscilloscope probes to the output of the lower bank driver. Adjust the settings on the oscilloscope to properly display the triggering pulse waveform. Test point 9. Triggering pulse input to lower bank driver AC. Identify the triggering circuit within the UPS. Connect the oscilloscope probes to the output of the upper bank driver. Adjust the settings on the oscilloscope to properly display the triggering pulse waveform. Test point 10. Triggering pulse input to upper bank switching transistor AC. Identify the switching transistor in the UPS circuit. Identify the gate for MOSFETs or base for bipolar junction transistors. Terminal of the switching transistor. Connect the probe of the CRO to the gate or base terminal of the upper bank switching transistor. Adjust the settings on the CRO to properly capture and display the triggering pulse waveform. Test point 11. Triggering pulse input to lower bank switching transistor AC. Connect the probe of the CRO to the gate or base terminal of the lower bank switching transistor. Adjust the settings on the CRO to properly capture and display the triggering pulse waveform. Inverter section. Test point 12. DC input to inverter section, upper bank. Identify the upper DC input section of the inverter. Set the multimeter in DC voltage mode. Place the multimeter probes at the DC input terminals of the inverter section with the correct polarity and measure the voltage. Test point 13. DC input to inverter section, lower bank. Identify the lower DC input section of the inverter. Set the multimeter in DC voltage mode. Place the multimeter probes at the DC input terminals of the inverter section with the correct polarity and measure the voltage. Test point 14. Output inverter voltages at transformer secondary tapping. Identify the secondary side of the transformer in the UPS unit. Set the multimeter to measure AC voltage with an appropriate range. Place the multimeter probes across the secondary side terminals between the tappings to ensure you get the desired output voltage. Recap. In this video, so far we have discussed how to identify various sections of UPS and locate test points on the circuit boards. Measure the voltage or waveform at various circuit boards in UPS. Thank you for watching. Hi everyone, in today's video, let us learn how to perform load test to measure backup time. Objectives. At the end of this video, you will be able to Number 1. Perform load test of battery using UPS. Number 2. Measure the backup time of the UPS with battery. Let us collect the tools and equipment required to do this practical. Trainees Toolkit 1 set. Computer UPS around 600 volt ampere with operating instruction manual 1 number. Digital multimeter with probes 1 set. Voltmeter 0 to 30 volt DC 1 number. Safety gloves 1 number. Stopwatch 1 number. 100 watt by 240 volt incandescent lamp test lamp 1 number. 12 volt by 7 Ah maintenance free rechargeable battery 1 number. Single phase variable lamp load 500 watt. 240 volt each 100 watt lamp 1 number. Procedure. Step 1. Make sure the UPS is turned off and unplugged from the power source. Step 2. Unscrew the outer cover using the appropriate screwdriver and gently slide out the cover from the UPS unit. Step 3. Identify the battery terminals and their polarities in the UPS unit. Step 4. Set the multimeter in DC voltage measurement with appropriate range. Make sure the range you select is higher than the voltage you expect from the battery. For example, if you are measuring a 12 volt battery, select a range higher than 12 volts. Step 5. Connect the positive terminals of the multimeter to the positive terminal of the battery. Connect the negative terminal of the multimeter to the negative terminal of the battery as shown. Step 6. Note down the readings in the tabulation. Serial number 1. Inverter status. Off. Battery voltage. 12 volt. Connected load. No load. Step 7. Connect the lamp load terminals to the output terminals of the UPS. Step 8. Switch on the UPS. Make sure the UPS is not connected to the input mains. Step 9. Switch on 100-watt lamp at the variable lamp load. Start the stopwatch and record the readings in the tabulation. Step 10. Keep monitoring the multimeter on the display of the multimeter. You will see the voltage of the battery decreasing. And halt the stopwatch when the lamp in the UPS glows with a beep sound, indicating the battery is low. Serial number 1. Inverter status. On. Battery voltage 12 volt. Connected load 100 watts. Stopwatch start timings. Stopwatch end timings. Step 11. Increase the load up to 200 watts from the variable lamp load. Start the stopwatch and monitor the display of the multimeter. Halt the stopwatch when the lamp in the UPS glows with a beep sound indicating the battery is low. Serial number 1. Inverter status on. Battery voltage 12 volt. Connected load 200 watts. Stopwatch start timings. Stopwatch end timings. Step 12. Switch off the UPS from the tabulation. You will notice that the back time of the battery is decreasing as the load on the UPS is increased. As the load increases, the runtime decreases because the battery is being discharged at a faster rate to meet the higher power demand. Recap. In this video, we have discussed how to perform load test of battery using UPS. Measure the backup time of the UPS with battery. Thank you for watching. Hi everyone. In today's video, let us learn how to perform all above experiment for 3-phase UPS. Objectives. At the end of this video, you will be able to identify front and rear pound controls and indicators of 3-phase UPS. Measure the input and output voltages. Perform load test using lamp loads. Let us collect the tools and equipment required to do this practical. Trainees Toolkit 1 set. Number 2. 3-phase UPS with operating manual 1 number. Digital multimeter with probes 1 number. Safety gloves 1 number. Cotton waste 1 number. Incandescent 230 volt 100 watt 3 numbers. Pendant holder 3 numbers. Connecting wires as required. Hookup wires as required. Safety precaution. Step 1. Earth connection is critical before connecting the input supply. Hence, ensure proper earth connection. Step 2. Wait 5 minutes before opening the UPS to allow the capacitor to discharge after the UPS is switched off. Step 3. Do not keep open the terminal block cover while the inverter is on. Procedure. Task 1. Identify front and rear panel controls. Step 1. Note down and record the specification of the UPS. The rear panel usually houses the input power connections, where the UPS is connected to the mains power supply. Step 2. Draw the front panel of the UPS with all indicators and switch. The front panel often features a display screen or LCD panel that provides important information about the UPS, such as input or output voltage, current load, battery status, alarms, and system status. Step 3. Identify each indicator and control on the front panel and record the observation in the tabulation. Serial number 1. Name of the indicator and switch. Input supply indicator. Purpose. This indicator is an LED indicator that verifies that all three phases of the input power supply are present. Number 2. Online indicator. In this mode, the main supply is present and the UPS continuously converts incoming AC power to DC and then back to AC, providing a stable and regulated output voltage and frequency to connected devices. Number 3. On battery indicator. When the on battery indicator is illuminated, the UPS draws power from its internal battery system to supply electricity to connected devices. This backup power source helps maintain continuity of operations and prevent downtime during power outages or disturbances. Number 4. Overload indicator. The overload indicator illuminates or flashes to indicate that the UPS is currently experiencing an overload condition. This occurs when the total power drawn by the connected devices exceeds the UPS maximum rated capacity. Number 5. Fault indicator. The fault indicator illuminates or flashes to indicate the presence of a fault or abnormal condition detected by the UPS. These faults can include various issues such as internal component failures, circuit malfunctions, or environmental factors affecting UPS operation. Number 6. Battery charge level indicator. The battery indicator displays the current level of charge remaining in the UPS batteries. When the battery charge level falls below a certain threshold, the indicator may illuminate or flash to indicate a low battery condition. Number 7. Battery bypass indicator. The battery bypass indicator serves to inform users when the UPS is operating in bypass mode, where the load is directly powered by the mains utility supply without passing through the UPS internal battery system. Number 8. Load on UPS indicator. The presence of the load on indicator assures users that the UPS is operational and properly configured to supply power to connected loads. Number 9. UPS on or off button. The on or off button is used to control the main power supply to the UPS unit. Pressing the button activates or deactivates the UPS, allowing users to turn the unit on or off as needed. Step 4. Identify and record the rear panel switches and connectors in tabulation. Serial number 1. Name of the switch and connect. Battery terminals. Purpose. Usually the batteries for the UPS are connected to the rear side of the UPS through battery terminals, marked with a positive or red color and a negative or black color terminals. Number 2. Input terminals. There are input terminals for each of the three phases R, Y and B. These terminals connect to the respective phases of the incoming AC power supply. Additionally, there will be terminals for the neutral connection N. Number 3. Output terminals. There are output terminals for each of the three phases R, Y and B. These terminals connect to the respective phases at the input of the load terminals. Additionally, there will be terminals for the neutral connection N. Number 4. Input switch. A 4-pole circuit breaker MCB has 4 switching mechanisms that can simultaneously open or close all three phases R, Y and B, along with the neutral conductor. The input switch allows for complete isolation of the UPS from the incoming utility power source. In case of an emergency or maintenance requirement, the input switch provides a means to quickly and safely shut off power to the UPS. Number 5. Output switch. Similar to the input switch, the output switch is also a 4-pole circuit breaker MCB, which provides a means to isolate the UPS from the connected critical loads. This isolation is crucial for maintaining and servicing, allowing technicians to provide on the UPS or connected equipment safely without the risk of exposure to live electrical circuits. Number 6. Battery fuses. In the event of a short circuit or other electrical fault within the battery circuit, the fuse will blow or trip, interrupting the flow of current and preventing damage to the batteries and associated components. Number 7. Manual bypass switch. By bypassing the UPS system, the switch allows electrical power to flow directly from the input source to the output loads, ensuring continuity of power supply even when the UPS is offline for maintenance or servicing. Recap. In this video, we have discussed how to identify the front and rear mount controls and indicators of the three-phase UPS. Thank you for watching. Hi everyone, in the last video we discussed how to identify the front and rear mount controls and indicators of the three-phase UPS. In continuation of this, in today's video we are going to discuss how to measure the input and output voltages and perform a load test using lamp loads. Procedure. Task 1. Measurement of the input and output voltages. Step 1. Open the rear panel cover of the UPS under supervision. Step 2. Switch on the input and output switch. Step 3. Switch on the inverter of the UPS. Step 4. Set your multimeter to the appropriate voltage range to measure three-phase lines and phase voltages. Step 5. Identify the input terminals on the UPS where the utility power source is connected. These terminals are usually labeled or marked as R, Y, and B for the three phases and N for neutral. Step 6. Connect the multimeter probes between the R and Y and B and R phases to measure the line voltage and note down the readings. Connect the multimeter probes between the R, Y, B and neutral terminals to measure the phase voltage and note down the readings. Step 7. In the same way, measure the line and phase voltages at the output terminals and note down the readings in the tabulation. Step 8. Set the multimeter in DC voltage measurement. Step 9. Identify the battery terminals on the UPS. Step 10. Place the red positive probe of the multimeter and touch it to the positive of the battery terminal. Then take the black negative probe and touch it to the negative terminal of the battery terminal in the UPS. Step 11. Note down the readings in the tabulation. Task 2. Performing load test using lamp loads. Step 1. Identify the load terminals at the rear side of the UPS. Connect the lamp load to the UPS output terminals. Step 2. Connect the three lamps, each one at every phase between phase and neutral as shown, like lamp 1 between R and neutral, lamp 2 between Y and neutral, and lamp 3 between B and neutral. Step 3. Switch on the input and output switch and start the inverter. Step 4. Check and observe the condition of the lamp load. Incandescent groups deliver core heat radiation, hence keep the lamp on a separate metal table with proper ventilation. Step 5. Switch off the input main supply now. The UPS load is under battery voltage. Step 6. Observe the performance of the load and battery voltage. Recap. In this video, we are going to discuss how to measure the input and output voltages and perform a load test using lamp loads. Hi everyone, in today's video, let us learn how to measure the displacement of a LVDT. Objectives. At the end of this video, you will be able to test LVDT coils using multimeter, measure the output voltages using CRO, measure displacement using LVDT. Let us collect the tools and equipment required to do this practical. Digital multimeter with probes, 1 number. Dual trace, CRO 20 MHz, 1 number. Function generator, 1 number. BNC cord for CRO, 2 numbers. LVDT trainer kit with manual, 1 number. Let us discuss LVDT. An LVDT or linear variable differential transformer is a type of sensor used to measure linear displacement movement of an object. LVDT consists of a primary coil, excitation coil, and 2 secondary coils, sensing coils, wound on a hollow tube. Inside the tube is a movable core, often made of a 2 ferromagnetic material. An alternating current, AC, is passed through the primary coil, creating an electromagnetic field around it. This field induces voltages in the secondary coils. When the movable core inside the LVDT moves, it changes the coupling between the primary coil and the secondary coils. As a result, the voltages induced in the secondary coils vary proportionally to the position of the core. Procedure. Task 1. Testing of LVDT coils using multimeter. Ohm meter. Step 1. Collect the required tools and equipments required for this exercise. Step 2. Take the LVDT and identify the primary and secondary coils by using its markings and positions. Step 3. Set your multimeter to the resistance ohms measurement mode at low range. Step 4. Connect the leads of the multimeter to the terminals of the primary coil. Note the resistance value displayed on the multimeter. This value represents the resistance of the primary coil. Coil, primary coil, resistance in ohms, secondary coil. Step 5. Connect the multimeter leads to the terminals of each secondary coil and note the resistance values displayed on the multimeter. The 2 secondary coils in an LVDT are typically connected in series opposition. Coil, primary coil, resistance in ohms, secondary coil. Step 6. The resistance of the primary coil in an LVDT is typically low, often ranging from a few ohms to a few tens of ohms. The resistance of each secondary coil in an LVDT is typically higher than that of the primary coil. It often ranges from tens to hundreds of ohms. Task 2. Measurement of output voltages using CRO. Step 1. Identify the terminals of the primary coil on the LVDT. Step 2. Connect the output terminals of the function generator to the terminals of the primary coil on the LVDT using BNC cables. Note: primary coil can also be tested using function generator by selecting 1 kHz sine wave frequency. Number 1. The positive terminal of the function generator should be connected to one terminal of the primary coil. Number 2. The negative terminal of the function generator should be connected to the other terminal of the primary coil. Step 3. Set up your CRO by connecting the probes or cables to the appropriate channels. You need to connect one channel, channel 1, for the primary coil and another channel, channel 2, for the secondary coils. Step 4. Connect the primary coil of LDVT to CRO. Number 1. Connect one probe of the CRO, channel 1, to one terminal of the primary coil. Number 2. Connect the other probe of the CRO to the other terminal of the primary coil using BNC connectors. Step 5. Connect the secondary coil of LDVT to CRO. Number 1. Connect one probe of the CRO, channel 2, to one terminal of the secondary coil. Number 2. Connect the other probe of the CRO to the other terminal of the secondary coil using BNC connectors. Step 6. Switch on the function generator and CRO. Step 7. Turn the knob or press the button to select the sine wave option. Adjust these controls to set the frequency to 1 kHz. Step 8. Place the core in the center of the LVDT by gradually moving the core from its initial position and observing the waveforms. Plot waveform in observations. When the core of an LVDT is in its center position, the output on the cathode ray oscilloscope CRO would typically show a straight line or baseline. This is because at the center position, the induced voltages in the secondary coils are equal in magnitude but opposite in phase, resulting in a null or zero output voltage. Step 9. Move the core in forward direction and observe the waveform, phase and magnitude. Draw the waveforms at maximum displacement. When the core of an LVDT is moved forward from its center position, it induces greater voltage in one of the secondary coils compared to the other. Specifically, if the core is moved forward from its center position, the output waveform on the CRO will typically show a positive deflection from the baseline. Step 10. Bring back the core in center and move the core in reverse direction. Observe the waveform phase changing and magnitude variation. When the core of an LVDT is moved in reverse from its center position, it induces a greater voltage in the opposite secondary coil compared to the other. Specifically, if the core is moved in reverse from its center position, the output waveform on the CRO will typically show a negative deflection from the baseline. Recap. In this video, we have discussed how to test LVDT coils using multimeter, measure the output voltages using CRO. In the last video, we discussed how to test LVDT coils using a multimeter, measure the output voltages using CRO. In addition to that, in today's video, we are going to discuss how to measure displacement using LVDT with an indicator. Procedure. Task 1. Displacement measurement using LVDT with indicator. Step 1. Connect the LVDT coils to LVDT signal conditioner, indicator or trainer kit. Signal conditioners for LVDTs usually have terminals or connectors labeled for the excitation voltage input, ground and the differential output signal in the trainer kit. Step 2. Place the core in middle of the LVDT or zero position in indicated scale. Gently move the core by hand towards the center position. Take care not to force it or apply excessive pressure, as this could damage the LVDT or affect its calibration. Step 3. Adjust the zero knob and make display zero. Identify the zero adjustment controls or knobs on the LVDT trainer kit. Use the zero adjustment knob to adjust the LVDT output signal until the display reads zero. Turn the knob slowly and carefully to avoid overcompensation or misalignment. After adjusting the zero knob, verify that the display reads zero when there is no input displacement or movement of the core. Step 4. incrementally move the LVDT core forward in steps of 5 mm. Continue moving the LVDT core forward in 5 mm increments until you reach a total displacement of 20 mm. After each 5 mm increment, note down the output reading displayed on the LVDT trainer kit. This reading corresponds to the displacement of the LVDT core from its initial position. As the LVDT core is moved forward, that is, away from the initial 0 position, the output signal typically increases proportionally. The output voltage or signal displayed on the LVDT trainer kit will typically rise as the core moves away from the 0 position. Step 5. Bring back the core in LVDT to the center position. Step 6. Incrementally move the LVDT core in the reverse direction, stepping back by 5 mm each time. Incrementally move the LVDT core in the reverse direction, stepping back by 5 mm each time. After each 5 mm decrement, note down the output reading displayed on the LVDT trainer kit. Continue moving the LVDT core in reverse in 5 mm increments until you reach a total displacement of -20 mm, indicating a displacement of 20 mm in the reverse direction. Step 7. Record the output readings corresponding to each 5 mm decrement of core displacement. Conversely, as the LVDT core is moved backward, that is, towards the initial 0 position, the output signal typically decreases proportionally. The output voltage or signal displayed on the LVDT trainer kit will decrease as the core moves away from the 0 position. Recap. In this video, we have discussed how to measure displacement using LVDT with an indicator. Hi everyone! In today's video, let us learn how to detect different objects using capacitive, inductive and photoelectric proximity sensors. Objectives. At the end of this video, you will be able to detect different objects using inductive proximity sensors. Detect different objects using capacitive proximity sensors. Detect different objects using photoelectric proximity sensors. Let us collect the tools and equipment required to do this practical. Trainee's Toolkit 1 set. Soldering iron 25 watts by 240 volt 1 set. Digital multimeter probes 1 number. Battery 12 volt 7.5 Ah 1 number. Inductive proximity sensor 12 volt DC 2 wire normally closed 1 number. Capacitive proximity sensor M18 NPN normally open NC 1 number. Photoelectric proximity sensors 5 VTC infrared 1 number. DC bulb 12 volt 5 watt 1 number. Connecting wires as required. Let us discuss inductive proximity sensors. An inductive proximity sensor is a type of sensor used in industrial automation to detect the presence or absence of metallic objects without physical contact. Inductive proximity sensors operate based on the principle of electromagnetic induction. They generate an electromagnetic field around their sensing face. When a metallic object enters this field, it disturbs the field, causing a change in the sensor's output. When a metallic object approaches the sensor's sensing face, it induces eddy currents within the object due to the changing magnetic field. Task 1. Detect different objects using inductive proximity sensors. Step 1. Identifying an inductive proximity sensor from its specifications involves understanding the key parameters typically provided in the datasheet. This indicates the maximum distance at which the sensor can detect the presence of a metallic object. It's usually given in millimeters or inches. Step 2. Two-wire inductive proximity sensors typically have only 2 terminals, one for the power supply and one for the output or load. Step 3. From the specifications, identify the positive and negative terminals of the sensor and the input supply voltage rating. Step 4. Connect the positive terminal of the battery to the positive terminal of the sensor through the load in series, like an alarm, lamp, buzzer, etc. with the correct polarity. Step 5. Connect the negative terminal of the battery to the negative terminal of the sensor. Step 6. Once the sensor is connected to the power supply and load, bring a metallic object within the sensor's detection range. Step 7. When the object enters the sensing range, the sensor detects it and completes the circuit, allowing current to flow through the load. Step 8. The load activates, signaling the detection of the object. The load can then perform the desired action, such as switching on a light or sounding an alarm. Step 9. Test its operation by introducing various metallic objects within its detection range. The detection range and sensitivity of inductive proximity sensors are optimized for detecting metallic objects, and they typically do not respond to non-metallic objects such as plastic, wood, or liquids. Let us discuss capacitive proximity sensors. A capacitive proximity sensor is a type of sensor used to detect the presence or absence of objects, including both metallic and non-metallic objects, without physical contact. Capacitive transducers find applications in various fields due to their ability to measure changes in capacitance, which can be influenced by a range of physical variables like pressure sensing, level sensing, humidity sensing, force and strain measurement, and fluid flow measurement. Capacitive proximity sensors operate based on changes in capacitance. Capacitance is the ability of a system to store electrical charge. When an object enters the sensing field of the sensor, it alters the capacitance of the sensor, triggering a detection signal. When an object enters the sensing field of the sensor, it alters the capacitance of the sensor, triggering a detection signal. The sensor contains an oscillator circuit that generates an electric field around the sensing area. When an object enters the sensing field, it changes the capacitance of the sensor by either increasing or decreasing it. The sensor detects these changes in capacitance and converts them into an electrical signal. This signal is then processed by the sensor's electronics to determine the presence or absence of the object. Task 1. Detect different objects using capacitive proximity sensors. Step 1. Identify whether the sensor is of the NPN or PNP type based on its specifications. For an NPN sensor, connect one side of the load to the sensor's output terminal and connect the other side to the positive supply voltage. For a PNP sensor, connect one side of the load to the sensor's output terminal and connect the other side to the negative supply voltage. Normally open NO. In a normally open capacitive proximity sensor, the output circuit remains open, non-conductive, when no object is detected within its sensing range. Normally closed NC. Conversely, in a normally closed capacitive proximity sensor, the output circuit is closed, conductive, when no object is detected within its sensing range. Step 2. Determine the voltage and polarity required by the sensor from its datasheet. Capacitive proximity sensors usually operate on DC voltage. Connect the capacitive proximity sensor to a DC power supply or battery and load with the correct polarity. Step 3. once the sensor is connected to the power supply, and load, if applicable, power on the system. Step 4. Bring an object within the sensing range of the capacitive sensor. This object should have a dielectric constant sufficient to trigger the sensor, example, plastic plus. Bring it very closer to the proximity sensor input and observe the display for any change. Step 5. As the object enters the sensing range, the sensor should detect it and activate its output, if applicable. Step 6. Monitor the output signal or the behavior of the connected load to verify that the sensor is operating correctly. Step 7. Test with various objects to verify the sensor's reliability and adjust settings if necessary. Recap. In this video, we have discussed how to detect different objects using inductive proximity sensors, detect different objects using capacitive proximity sensors. Thank you for watching. In the last video, we discussed how to detect different objects using inductive proximity sensors. Detect different objects using capacitive proximity sensors. In continuation of that, in this video, we are going to discuss how to detect different objects using photoelectric proximity sensors. Let us discuss on photoelectric proximity sensors. Photoelectric proximity sensors, also known as photoelectric sensors or photo eyes, are devices used to detect the presence, absence, or distance of objects by using light. They are widely used in industrial automation, manufacturing, packaging, and various other applications due to their versatility and reliability. Photoelectric proximity sensors use light to detect the presence or absence of objects within their sensing range. They consist of an emitter, which emits light, and a receiver, which detects the light. When an object interrupts the light beam between the emitter and receiver, it triggers the sensor's output. In this mode, the emitter and receiver are placed opposite each other with a gap between them. When an object passes through this gap, it interrupts the light beam, causing a change in the receiver's output signal. Task 1. Detect different objects using photoelectric proximity sensors. Step 1. Determine the power requirements of your sensor. Most photoelectric sensors operate on low voltage DC power, commonly 12 volt or 24 volt DC. Check the datasheet of your sensor for the specific voltage and current requirements. Step 2. Connect the power supply to the sensor. Typically, this involves connecting the positive terminal of the power supply to the positive terminal of the sensor and the negative terminal of the power supply to the negative terminal of the sensor. Step 3. Connect the load like a lamp or buzzer for indication when an object is detected as per the connection given in the datasheet. Photoelectric sensors usually have an output signal that changes state when an object is detected. This output can either NPN, sinking, or PNP, sourcing, depending on the sensor type. Connect the output terminals of the sensor to the input of the device you want to control or monitor based on the detection. Step 4. Position the emitter and receiver of the sensor so that the light beam emitted by the emitter is aimed at the receiver. Ensure that the sensing area covers the region where you expect objects to be detected. Step 5. Power on the sensor and verify that it's functioning correctly. You can do this by observing the output signal of the sensor. When no object is blocking the light beam, the output should be in one state, either high or low, depending on the sensor type. And when an object interrupts the beam, the output should switch to the opposite state. Depending on your application, you might need to adjust the sensitivity or other settings on the sensor to optimize its performance for your specific requirements. Recap. In this video, we have discussed how to detect different objects using photoelectric proximity sensors.
In a few minutes, I will be briefing on the topic soil stabilization techniques with prefabricated vertical drain. The purpose of the PVD technique is to stabilize and to strengthen the soil underneath. In this process, soil is stabilized through increasing the shear strength of this soil.